Hello, everyone. Today we're going to start our Physics 5341 class, Electrodynamics. So we're going to start lecture 1. And the textbook we're using is this one, the Classical Electrodynamics. And the detailed information are shown here and also in your syllabus. Okay, so for the first class, we're going to introduce some electrostatics. So in order to learn electrodynamic, we will start electrostatics. So there are several basic ideas or concepts in electrostatics, which helps us to review what we have learned before. And then from here, we will start to move on to the electrodynamics. So the first concept, Coulomb's law. Do you still remember Coulomb's law? Coulomb's law describes the basic fundamental concept of the forces between two charges. So if you have two charged articles or two charged points at a distance, then Coulomb's law helps you to calculate the magnitude and describes the direction of the forces between them. Okay, now let's review what we have learned before from Coulomb's law. Okay, let me switch my tool into a pen. Now, if you have two charges, let's say Q1 and another charge, Q2. So what Coulomb's law tell us? First, Coulomb's law tells us the force between the two charges varies directly as the magnitude of each charge. More accurately, we can say the force between them is proportionally to the magnitude of the charge. So it's proportional to the charge. So we can say the force, let's say F, is proportional to Q1 and proportional to Q2. So it has a relation like force is proportional to Q1 and proportional to Q2. Then it's proportional to Q1 plus Q2. Q1 times Q2. Number 2, inversely as the square of the distance between them. So the force is inversely proportional to the square of the distance, which is proportional to 1 over r square. This is the second rule. So the first rule is proportional to Q1 and Q2. If we consider both number 1 and number 2 conditions, you can write it in this way. Proportional to Q1, proportional to Q2, proportional to 1 over r squared. And then the third one is describing the direction. It's directed along the line joining the charges. And number 4 is attractive if the bodies are oppositely charged, and repulsive if the bodies are or the points are in the same charge. So this is describing the direction. The direction from Q1 to Q2 is repulsive or attractive, depending on if Q1 and Q2 have the same charge. So let's define the direction of Q1 to Q2 is r hat. Then we'll say F, the vector F equals to Q1, Q2 over R squared times the constant, and then times the direction from Q1 to Q2. So this is Coulomb's law. K is a constant. It depends on the units you're using, and it also depends on the material between Q1 and Q2. For example, in vacuum, K is a bigger number, but if it's in, let's say, water or some other materials, K is a different constant. And sometimes we also write the dielectric constant, or we separate a dielectric constant from the K and put it here, epsilon. We say epsilon to be the dielectric constant. And this dielectric constant describe the different materials. For example, in vacuum, it's 1. In some solutions like in water, the epsilon is 80. So this is the basic idea of Coulomb's law. The Coulomb's law describes the magnitude and direction of the forces between two charges. And then from the forces, we can derive another concept, which is electric field. Although the thing that eventually gets measured in a force, it is useful to introduce a concept one step removed from the forces, which is the concept of an electric field due to the array of charged bodies. So if we look at this picture from Q1 to Q2, of course, you can calculate the force. If you change the Q2 into a unit charge, let's say the charge is 1, then you can use let's say a unit charge to be a probe, put it here, 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 to measure the forces surrounding Q1. Then you will figure out the forces might be something like that. And when you move it far away from Q1, the magnitude becomes smaller. When it's getting closer, the force is getting big. And from there, we define the electric field, which is F equals charge times electric field, or electric field equals to force over charge. And then Coulomb's law can be written in this form again. Here we write it as Q1, Q2 over R squared times a constant times, let's say, a uniform or a normalized R, which is the direction of the Q1, Q2 connecting line. So R is just a unit vector, which describes the direction. So in this form, the electrostatic force can be described in this format still. K is a constant, Q1, Q2, they're scalars of the charge 1 and charge 2. And then x1 subtracted by x2. x1 describes the position of the first charge. If we write the first charge to be Q1 in a coordinate system, let's say this is origin, we can say the position of the first charge to be x1, it's a vector. So if you see this is bald, forward, found, that means it's a vector. And then the second charge, let's say it's here, x2, a vector. X2 describes the vector from origin to this position. And then x1 subtracted by x2 is a connecting vector between x1 and x2. So this is x1 vector subtracted by x2 vector, because here is a vector, here is a vector, here is a vector, here is a vector. So x1 subtracted by x2 is a vector between x2 and x1. x1 over x2, and then x1 subtracted by x2 over the magnitude of x1 subtracted by x2 cubic means the magnitude of this vector's cubic value, or it can also be written in k q1, q2 times 1 over x1 subtracted by x2. It's a vector subtraction. And then it's a magnitude squared times the direction of r, or the direction of x1 subtracted by x2. Let's say hat. Hat means a normalized vector. Let's say the magnitude of this vector is 1. Or we can simply make it, we can define the direction to be r, or any symbol you want to use to be a direction vector. The unit, the magnitude of its value is 1, but the direction describes the direction from x1, from x2 to x1. They are the same. Okay, and then if this is a force, and then the electrostatic field or electric field at this point can be calculated in this equation. Let's say the reference is still x1. If you want to calculate the electric field between, let's say, x, this is x point, between x and x1, then you can use this equation. The force over charge equals to electric field. So this is a way of calculating force and electric field. And when you do the calculations, you need to be careful with the unit, of course. There are two different unit systems when you do the electrostatic calculation. One is using the stat column, and then the other one is using SI unit. Please read the textbook and see what's the difference between them. Now, next concept. For multiple charges, there's a superposition rule. What is that? For example, when you want to calculate the electric field or force, let's take an example of electric field for multiple charges. Let's start it from a single charge first. Now we have one charge, Q1. If you want to calculate, okay, so the coordinates of x1 of Q1 is x1. Let's say it's in a coordinates system like that. I'm using the mouse to draw the picture, so the picture might look not so good, but it's just simple pictures. I guess you can understand. For example, you have charge Q1 located as X1 position. If you want to calculate the electric field at some position X, then, sorry, it's not a good picture. Okay, now what you can do is you do a connection between X1 and X, and then that's the direction of Q1. That's the direction of E, or electric field generated by Q1. You can calculate it by using the equation. Let's say E X equals to a constant times Q1, because it's generated purely by Q1, and then X subtracted by X1, and they are all vectors. So it's a vector calculation, and then we only take the magnitude of the two vectors, cubic, because it's cubic, because you will have X subtracted by X1 here. So essentially it's generating so this over this, it's generating 1 over R squared, because it has the magnitude of the vector above, and it has a cubic of the vector between X and X1 below. So one of them will be canceled. So this is EX generated by Q1. Now, if you have another Q or charge, Q2, then what's the electric field at the position X? It's easy. So you draw a line between Q2 and X. Then you will have electric field generated by, let's say this is E1, this is E1, this is E2, which are generated by Q1 and Q2. You can do a vector sum of E1 and E2. Then this is E1 plus E2. So the superposition rule tells us if there are two charges, then the electric field can be calculated by first calculating E1 and then calculating E2, and then summarizing or summing E1 and E2, you will get the final electric field at this position. And then EX equals to this plus K times Q2 times X subtracted by X2 over X subtracted by X2 cubic. And then if you have more than two charges, it's the same thing. You just add all of the these electric field terms one by one and do a vector sum. This is so-called superposition rule, which is described here. So this part could be considered as the constant, and then a sum of all the electric field by individual charges. Okay, and then if the charges are so small, so from equation 1.4, each charge is a point charge. So you can do the calculations by sum them. by summing up them. But if they're not point charges, they are very small charges. The charges are so small and so numerous, and they can't be described by a charge density. Then what can we do? We can change the sum into integral, which is shown here. So rho becomes the density, and it's a function of x. This time let's define x as x prime to distinguish the integral case and the point charge case. So by doing this integral, you can calculate also the electric field, and of course you can also calculate the electrostatic force by using Coulomb's equation. And then once we define the integral and the charge density, at this point, it's worthwhile to introduce Dirac delta function. In one dimension, the delta function can be written as a delta x subtracted by a. It's a mathematically improper function having the properties of this. First, the delta x subtracted by a equals to 0 when x is not a, and it equals to the integral of this equals to 1 if the region of integration includes x equals to a, and then equals to 0 otherwise. So if you draw the picture of delta function, it is something like this. It's a very sharp peak at a. So if it's not equals to a, then the function, delta function, equals to 0. When x equals to a, actually the value should be infinity large. But if you do the integral means you calculate the area below this curve, below the delta function curve, then the integral equals to 1 if your integral includes the region of a. Otherwise, if you do the integral outside x equals to a, it's always 0. So that's delta function. And then for arbitrary function fx, if you do an integral of fx times delta function and x, and it equals to fa if the integral is in the region which includes a, x equals to a. Otherwise, it's 0. So this is understandable. So if you multiply this delta function by another function and do the integral, if there's no function, no fx, then the integral should be 1. If you have fx here, the integral should be fa, which is the value of fx at a. That's easily understandable. And number 4, number 5, we don't have to pay attention on that. It's out of our course. We don't have to use those functions. And then if it's not one dimension delta function, let's say it's a multiple dimension delta functions. For example, here it shows 3-dimension functions. Then what we can see from the delta function is, let's say here it's not a anymore, it's a x. X is a 3-dimensional vector. Then delta x subtracted by this capital X equals to delta function x subtracted by x1 capital and then another delta function in x2 direction, another function in x3 function. And this is in the Cartesian direction or coordinates. Let's define these three directions to be x1, x2, x3. Then a three-dimensional delta function could be written in the product of three one-dimensional delta functions in the 3D directions. And then if you do the integral of a delta V or a volume integral of this three-dimensional delta function, it equals to 1 if your integral contains x equal to capital X, and it equals to 0 if it doesn't contain the capital X point. Let's say in a three-dimensional case, you have one point here, which is capital X. If your volume function, if your volume integral contains this this point, then you get 1. Otherwise, if you do an integral here, then it equals to 0. And a discrete set of point charges can be described with a charge density by means of delta function. For example, rho x can be written in qi times delta function of x subtracted by xi, which describes the, let's say, if you have a qi here, and then you have the coordinates is xi, qi, xi, then qi times a delta function of x subtracted by xi should be the point charge of qi. This is density. When you do an integral, the density becomes a charge, which is qi at position xi. And then the same thing for some other x and q's. For example, q2, x2, and of course x, there are vectors. So this is the, let's say, discrete set of point charges written in the format of delta function. Okay, that's it for today's class. We just introduced some basic ideas from electrostatics. So please read the textbook, because we're not going to cover everything in the textbook. If we see something is very easy or something is beyond our course, we will not describe them in the lecture, because the lecture time is very limited compared to the content of this book. This book actually described a lot of details. So please read the book carefully before each lecture and after each lecture to learn more details from the book. Okay, thank you guys. I'll see you next time.